Welcome back again. We are on board for another amazing presentation. This one is from Michael Wolfe. He's the compiler engineer at the Portland Group / Nvidia. Here you go, Michael.
All right, so as most of you probably know, PGI was acquired by Nvidia, or vice versa. So I am, in fact, an Nvidia employee, but we're preserving the PGI brand and the PGI products. So I'm here speaking as a PGI compiler engineer. And I've been giving this similar talk at this booth for the past couple of years. There's only a few new things this year, but for some of you that are not entirely familiar with the subject, this is our abstraction of the HPC compute node of the future. And it's got two sides. You have your host side and you have your device side. High performance multi-core hosts with some number of cores, 8, 12, 16, or what have you, with a latency optimized memory. So the bandwidth here is not very good, but you've got 2 or 3 level cache memory here so that the average latency is low. And then you have a bandwidth engine over here. So this is optimized for a different sort of problem, highly parallel. You've got a lot of parallelism over here. So you got MIMD parallelism in this direction, and if you don't know what that means, you're in the wrong conference. And SIMD parallelism in this dimension. And there's multi-threading parallelism on top of that. And you have a stream or a bandwidth optimized memories. So there are caches, hardware and software caches, but relative to the cache size over here, these are tiny. So they're really not going to be very much good for temporal locality. I had to go back to my architecture lectures here. But the bandwidth is high, and the memory can keep up with the performance demands of this highly parallel engine. Clock rate over here is slow, typically 1/3 to 1/4 that of the host. It doesn't issue as many instructions in parallel, maybe dual instruction issue where this would be 3 or 4 or 5 instructions per clock. No out of order execution. A lot of the advanced architectural features that exist over here and require a heavy duty control unit just don't exist here because they're using those transistors in the compute units, in the floating point units or your functional units. Now we can take a GPU and we can map it onto this. An Nvidia GPU, these would correspond to the SMs. And inside here, these are the CUDA cores inside an SM. You can take a Xeon Phi, these would be the cores and the vector unit. You can take an AMD Radeon, these would be the compute units and the vector units inside the compute units. So they all have those 2 levels of parallelism, and there's a reason for that. SIMD parallelism because it's cheap. For a relatively small increase in the number of transistors, you get a relatively significant increase in the performance. And MIMD parallelism because not everything is SIMD, so you need that. So they all have the same solutions to the problem because basically there aren't that many solutions you can use. Now there are other memory organizations one can use. The separate memory that we saw before is what we're seeing today. You can imagine where you've got one big system memory and this uses a subset of the system memory. You can imagine another, well this would be the golden case where they're actually both using the same memory. And you'll see some of these either today or in the near future. The problem you have today with today's system memory is, well, where's my high bandwidth interface? These are not high bandwidth memories today. Question? So he's asking, is this AMD's HSA architecture? And that would map onto this, right? We have one system memory. Now, in the future, we're going to see high bandwidth memory interfaces, stacked memory or Micron's hybrid memory cubes. And so maybe we can actually get enough bandwidth out of the memory to support the bandwidth engine with low enough latency optimized caches to support your latency engine. Another one, which I don't have a slide for, is imagine dividing this in half, so it's a separate memory again, but a single virtual memory. So you have separate physical memories, a bandwidth optimized physical memory, a latency optimized physical memory, the same virtual address space, so each device can access either memory. There's a performance penalty if you're going the wrong way in either direction, but it all works. Rather than doing data copying between the two, you're just placing the data in the right place, hopefully, or moving the data to the right place, either in software or hardware. So what I'm here to talk about is OpenACC, and I'm assuming most of you, well, many of you, or at least some of you, have heard of OpenACC and maybe even have some familiarity with it. So the idea behind OpenACC, it actually came from the PGI accelerator model that goes back, I guess, 5 years now. It's directive-based programming to target accelerators where the execution model maps onto that engine we just saw before. And so there are two types of directives. There are data directives that control when data moves or copies from the host and the device, when it gets allocated, when it gets moved, when it gets updated between the two. And then compute directives that tell what code will actually execute on the device. So these are intentionally similar to OpenMP directives. The syntax is similar, the syntax rules are similar, but we have these data directives as well. And in this case, I've got some sort of iterative 9-point stencil written in C, and I'm telling it to run the I loop in parallel across the device. And the compiler, if it's smart enough, can also parallelize the J loop or vectorize the J loop. And I'm telling it to copy the array B, and then A is just a temp, so just create the array A, allocate it, but I don't need to copy any data. And then here I'll swap pointers and do the loop again many times. And one of the nice features of OpenACC is those. Let me come back to that slide. This is the right order. So OpenACC is an open specification. There are several commercial vendors in addition to PGI. There's CAPS, which has a booth up there somewhere, and Cray, which I've forgotten where they put their booth. And now there are several open source implementations underway. There are 2 projects putting OpenACC into GCC, and there are at least 3 other open source projects working on OpenACC implementation. So we support all that. And if any of you are interested in those and you have questions about the specification or how to implement certain things, we'll be glad to answer your questions. Okay, I said all that, and then we've released the OpenACC 2 specification this past summer. There are implementations from Cray available now, from CAPS available soon, and PGI will be rolling out the 2 OpenACC 2.0 features over the coming years. The most important feature is procedure calls, and we couldn't really support procedure calls until we had a linker, and now at least the Nvidia device has a linker, so we can support that. Separate compilation of procedure calls, that's the most important feature of high-level language programming ever. I mean, you can't call it high-level language programming unless you can have procedures and libraries. Nested parallelism is supported. Now, I don't really think nested parallelism per se is a natural fit onto these accelerators because they already have a lot of parallelism. But you can imagine I want to take that scalar thread from the host and move the scalar thread to the device and have it launch all the parallelism on the device. Then the host can go do something else, completely decoupled from the execution on the host. Well, that's basically nested parallelism, except the first level is really just scalar. And there are a lot of other features as well. And here's the workflow. So the program build looks just like the build you have now. If you use make, you just type make. You put an extra flag on the compiler. The compiler, as with the CUDA compiler, generates host code and device code. Now, PGI, we are a native compiler, so we actually generate the assembly code for the host. And then for the Nvidia GPUs, today we compiled to CUDA C and then use the CUDA C toolkit to compile that down to a CUDA binary. This coming year, we're going to be using their LLVM interface, and so we'll be compiling using that directly to PTX. Package it up into a single object file. It gets linked up into a single executable, so that you can put these things in libraries. You can. It works just the way that your classical execution flow works. Okay, here's the question back here. What other targets do we support? Well, this talk is about the Nvidia implementation. If you want to know about other targets that we support, come to our booth, which is down there, or go to the 3 o'clock talk at the booth next door. Okay, so this is back to our coding example. The nice thing about this is those data directives don't all need to be visible at the point that I'm computing it. So, in fact, the most successful cases are where you put the data directives and do the data allocation in the main routine or at some outer level. And you can do all the compute anywhere. The data lives on the device, and the compute happens on the data that you moved over to the device. And it can be quite successful. In fact, the #1 bottleneck to high performance on these is managing data traffic between the two, the host and the GPU. And so that's new to this world. And if we come to different architectural designs where they share memory or they have some other memory architecture, that may become less important for the programmer to take charge of. We would like that to be the case, but I have nothing to say about that. And why OpenACC? Why have directives at all? Why not just program in CUDA or OpenCL or some other set? And the key, when we were designing OpenACC, it was a committee design. It wasn't just PGI. I mean, we started with the PGI model, but we added things and threw some things out and changed others. But the intent was to have a programming model that supports performance portability. And what is performance portability? It's one program that not just runs on different devices, but runs well on different devices. So the programming model has to support the implementation that can change the execution behavior depending on the characteristics of the target architecture. And that depends on a certain amount of smarts in the compiler and the runtime, and it depends on flexibility in the execution model. For instance, okay, so you're saying portability also means portability across vendors, across implementations. And that's a good point. And so you want to have the same source code, not just by PGI, but by Cray, by CAPS, by the GCC implementations. Okay, and you're going to ask about Intel, and good luck with that. So. That's a separate discussion, so I'm not even going to repeat that because it was non-complementary to another vendor. So, the directive model we have here allows the compiler to map the parallelism in the program that's either specified by the programmer or discovered by the compiler onto the parallelism of the device. So you think NVIDIA, you've got in the programming model, we have these MIMD and SIMD dimensions, but in the details, we have these streaming multiprocessors, and you've got SP units, you've got DP units, you've got load store units, you've got the shared memory to manage. And so the compiler has the flexibility to say how much parallelism in each dimension is, and how do I map that onto these devices. If I'm compiling for a different device, think of a Xeon Phi. You would have totally different numbers and different level of implementation. This year, we're also going to be working on compiling the OpenACC just to a multi-core. Well, obviously you want that. Why don't you have it already? Well, you know, that's a resource commitment issue, but we're committed to that. And you would have a totally different sort of parallelism mapping onto a multi-core host. And I have plenty of time, so I can slow down. Okay, a couple things about performance. This actually is an old study that we did, and there's an article on the Portland Group website, pgroup.com. If you look at the PG Insider articles, one of our engineers took this code, and it's described very nicely, and I won't even try to describe it. And he tried to speed it up using OpenACC, and his experience was somewhat common to many initial implementations. You add some directives, and your performance goes way down. And why? Well, it's the data part. You're transferring data too often, too much data too often. So he spent 5 hours working on this. He had several steps that he went through, basically a series of 5 steps. They're described in the article. And this, he was comparing performance against, looks like 8 cores, 4 cores, 2 MPI processes, 2 threads per process. And time was running about 1,000 seconds. And then he initially added some directives, and performance didn't look very good, slowed down by a factor of 3. You spent 10 minutes for a factor of 3 slowdown. Then he spent the next hour working on those data directives. What data should belong on the device? Where should I move it to the device? This actually is a hard problem. Now, it's a hard problem in the sense that the compiler cannot do this for you. It not only requires whole program analysis, it requires some thinking. So these directives are easy to write, but they still require you to think. All parallel programming, you have to think. Nobody is relieving you from having to think. You'll see out here in the world, say, use our model, this makes parallel programming easy. And you see that quote several times around here. They're all lying. You cannot make parallel programming easy. You can make parallel programming easy if you don't care about performance. If you just want to write a parallel program, that's easy. just put a big parallel for loop around your whole program, and there you're running in parallel. You're doing the same thing redundantly. Okay, you're not getting any performance benefit whatsoever. It's stupid. You can make writing the program easy, but the programming involves more than just inserting the directives. It's how do I organize my program so I have the right style of parallelism? How do I organize my data structure so the data is laid out in a way that takes advantage of that high bandwidth memory, for instance, or caches or whatever features of your architecture you have? That's a creative process that the human is in the loop. So that's unfortunate for some of us because it means you have to think, but it is fortunate because it means you'll still have a job. We're not going to automate your job. So anyway, he spent an hour on that, and he got, well, okay, a factor of 2 speed up almost. Then he spent some more time optimizing loop directives and optimizing the schedules, and he actually ended up, after 5 hours, with a nice speed up of a factor of 5. Now, I can't guarantee you're all going to get a speed up of 5 in 5 hours, but this was a nice piece of work. Another example, so Cloverleaf is a mini app from the Atomic Weapons Establishment in Great Britain, and this was work that we had nothing to do with. They did it themselves, and these numbers come from them. So they took the Cloverleaf mini app and they ran it in a bunch of different configurations. And here this is running on a dual socket, and I've forgotten how many cores, dual socket Sandy Bridge, OpenMP parallel, and you're seeing performance execution time. So lower is better here. And he's comparing the CUDA and the OpenACC implementations against the OpenMP on the multi-core. And you notice he doesn't show the OpenMP times over here because they go off the top of the chart. And so what we're seeing here is nice performance benefit for this application against OpenMP parallelism, and nice performance compared to CUDA as well. Now, okay, granted this is a log scale, so this difference is probably a large factor, but still, it's we're reasonably happy with this performance. And the other thing that they measured was they did this using OpenMP, OpenACC, CUDA, and OpenCL. And they counted how much effort was it. How do you measure effort? Well, they didn't count lines of code, they counted words of code. How many words of code did they have to add to the program to make this thing run? I think they're doing another presentation of this here at this conference as well, so with some newer numbers than this. And they found OpenACC is more productive in the sense that less work than CUDA or OpenCL. And they did a study of what's the difference between OpenCL and CUDA, because basically their execution model is the same and their kernel programming model is the same. But this was the management, the API calls to build and load, to attach to the device and build and load the program and just get the thing going. So that does, with bigger programs, this does not scale up. So the question is, do we have plans to support the OpenMP 4.0 device directives? Let me come back to that. I'll finish my presentation and answer that. There's a lot of OpenACC porting activity around the world. Frankly, as it says here, most of this today is in Fortran, although some in C, C++, not very much in real applications yet. There are some features missing from OpenACC that we know are missing that are needed to support real C++ codes, and we're working to design those into the next version of the specification. So there's a lot of work, a lot of different stuff, and these are not from the vendors, these are from real users of different compilers. Okay, so this is our key missing feature, and what we're working on for the next version is support for C++ and members of structs and classes and derived types in Fortran. So array members. We have one of our users. We had an OpenACC workshop, and we had a user day, and they came in, and one of the users came in with, this is a Fortran code, and he had an array that had a derived type, each element of which had an allocatable array, which was a derived type, each member of which had an allocatable array, a member that was an allocatable array. So it was this whole big nested tree of data structures. They just wanted to take the whole thing and put it over on the device. Well, we never predicted that, so we weren't ready for that. And now you can imagine in C, well, everything is a class member. Okay, not everything, but basically, in real C programs, everything is a class member. So the real arrays are class members. And what's the most important array in C++ codes? STL vector. And what's the name of the STL vector array? Well, you can't tell because it's private into the STL data type. And you can't change that header file. So that's a real challenge if we wanted to say, move this vector to the device, but moving the vector doesn't mean move just the class, it means the class and everything it points to. That's a challenge, and we're working on that. And we know it's important, and so, okay, there we go. And some other things that we're working on as well. Okay, so these are the highlights of PGI 2014 compilers. We're keying on performance portability, and if you come to our booth, we'll demonstrate what that means, or I have a vendor exhibition talk at, I think, very late on Thursday, probably 2:30 or later on Thursday, which means same program running well across different devices. And we have been claiming that this was how it's designed, and now we can claim, we can demonstrate that. We're working on the OpenACC 2.0 features. There are other implementations that have are ahead of us in terms of features, but that's okay. And performance optimizations. We have some interesting. Well, this is where compiler guys really like to work on, because you get into it and you do something really cool. And we also have other features working on devices. CUDA Fortran. If you're a CUDA programmer and you're a Fortran programmer, CUDA Fortran is your answer, because it's just CUDA in Fortran. If you're a C programmer, this is really of no interest to you. There's no advantage to it, particularly over CUDA C, except for the advantages of Fortran over C in general. And we'll be having debugging for CUDA Fortran in early 2014 and debugging for OpenACC later on in 2014. Okay, this is the end. The question, open question was, will we support the OpenMP 4.0 device additions in the OpenMP 4.0 and not in the near term? And the reason being this. Performance portability. OpenMP is a well-established standard and works well on multi-core CPUs and multiprocessors. And when you think about the execution model for OpenMP, that goes back, well, actually more than 20 years, because OpenMP is derived from prior things, where you have some fixed number of processors or cores. The numbers are typically single digits. Now we're seeing low double digits, so not very much parallelism going on. And that's the mindset of the specification. You create the number of threads you want, and you're stuck with that number of threads. And taking that and putting that model onto a device where you need 1,000-way or 10,000-way or 50,000-way parallelism, it's not a very good match. So OpenACC gives more flexibility to the implementation. It does not have all the features of OpenMP, and we make no apologies therefore. But it does allow us to claim and now deliver performance portability that I don't think OpenMP 4.0 device extensions will do. So that's the long answer to that question. Other questions?
And Michael, we have a question from online.
I have a question from online. Read it for me.
Yes, it is. Can OpenACC 2.0 use the new CUDA 6.0 unified memory feature? So, okay,
there's two sides there. There's nothing in the programming model of OpenACC specific to CUDA. So if you say, can I use CUDA this in OpenACC? Well, they just don't relate. It would be like saying, can I put grape jelly on my potato? You know, they just don't, it's not in the same sentence. But can an implementation use the unified memory in an OpenACC program? And an implementation could, and we're exploring how to use that in the PGI implementation. Where's the camera? Is that the camera? See, I should look to the camera. So in our implementation, we'll be exploring how to do that. We just don't have that yet. Other questions? No.
It seems to me that in terms of performance portability, that OpenACC and OpenCL share a lot of goals. Can you kind of comment on how that might shape the future of OpenACC?
So I would say that's absolutely wrong. OpenCL does not claim nor deliver performance portability. OpenCL had a tough problem to try to solve, right? Writing a program that will work on these devices, and you don't necessarily know what device you're running on when you're writing the program. So they have a lot of these features like the runtime compilation, JIT compilation, which is built into the model, the language, and all the implementations. That's just the way that it works. And the execution model is very similar to CUDA, and intentionally so. But since they don't have a compiler for the host code, all the host API has to be done through function calls. And so that's an unfortunate side effect of their restrictions on their implementation. But as far as performance portability goes, if you really nail down the OpenCL experts, and there was a nice article recently, actually, in HPC Wire, I think. No, it was an article linked to from insideHPC, and was talking about performance portability in OpenCL. And there was an interesting quote in there, and I don't get it quite right, but he said, I mean, yeah, you have to rewrite your kernel for each device, but isn't that exactly what you want to get the best performance? And the key word there is kernel, singular. Because these OpenCL programmers, the real OpenCL programmers, are in the embedded world, right? Because that's where you're doing computing on the device. You don't know what device you're on, and the guy next year he'll have a new cell phone, it'll have a new device. So, but they're focused on one kernel in particular. They've got some particular application that needs one particular thing, and so they're all focused on one app. Well, we have big programs, okay? So the OpenCL model, I think, does not address that.
All right. Well, we do have a question.
Will the recent announcement of OpenACC supporting GCC change something for PGI in terms of the marketing or open?
So how does the GCC implementation of OpenACC, and there are others, there are at least 3 other open source, and we love this. For us, our purposes, this means more availability of OpenACC compilers will drive more experimentation and adoption. And when they start adopting OpenACC, then they'll want a good compiler that they're willing to pay for. Okay, that was a low blow. But this is the rising tide floats all boats. So more users just means more customers for us. In fact, we would love, if, as I said early on, if there are open source implementers that have questions, we'll be glad to help you out. Well, we'll give you advice anyway. I'm not going to write any code for you.
All right. With that, we are going to thank Michael.
Thank you very much.
Also mention that the PGI booth is 2509, right? So definitely go by and visit Michael there. We're going to take the next couple of minutes and get ready for